Good evening, everyone. So, welcome you all to the live session 11 of NPTEL course. We will start in few minutes. We'll wait for others to join, then we will start. Okay. Okay. So, when you see the energy storage application, so let me tell you the reason behind the need of the energy storage. Why do we need energy storage? So basically, to supply energy reliably and efficiently. So basically, what is that key? We have this energy demand curve, that is demand of the power at that time of the day. So we see that key when we have this, there's some time in the day when the energy demand is quite low, while sometimes the energy demand is quite high. So there is fluctuation in energy demand, and basically also the renewable has this power production is fluctuating depending on the sources like solar or wind, because they are not continuous supply, they are intermittent in nature. That's why this fluctuating demand requires energy storage devices to integrate with this type of system. So that is why we are basically studying thermal energy storage system. Okay, so what is the meaning of diurnal here? Diurnal is basically day and night both, considering the variation of day and night. So this is how the diurnal power produced by renewable sources over a typical sunny day. Okay, so most of the power is produced between 8 a.m. to 4 p.m. Okay, so this is what, and this is the power production. Okay, from 8 to 6, and this is the curve for demand. So you can see demand is continuous with some variation between this region, but the power production for this region is zero. So you need to store the extra energy, that is this, so that it can be supplied to this region. This is the main reason for energy storage. So these are the various factors like temperature, energy density, minimum heat loss, cost, environmental impact, efficiency. These are some of the factors which are considered for energy storage system. Similarly, there are different types of energy storage system like thermal energy storage, electrochemical storage, pumped hydro, compressed air, energy storage by flywheels. Okay. So I won't go into detail like what is the need, because I discussed itself that the intermittent nature is what requires the energy to be stored so that it can be utilized throughout the day. And the load variation is actually fluctuating throughout the day. So not only the energy produced is variable, but also the load itself is variable. So like imagine when you are at home. So when do you need most amount of electricity? Definitely in summer season, people will need more electricity in the afternoon time because they are running more ACs. In the evening time also, when people come back home, they run TV, lights, everything. So in the evening also, the energy demands actually goes up. So this is how it works. And the size is basically size of a storage system is largely determined by the specific purpose for which it is used. Okay, so please see this slide. This slide is very much important. Okay, and if you have any question, please ask, because this slide actually explains the type of storage which we are going to use and the variation of the energy demand and everything. Okay. So you guys got idea what is buffer storage, diagonal storage, and wall storage? So basically for buffer storage, energy requirement is essentially the same as the production. Okay. So storage energy for short interval time is small in size. Dynamic storage load demand is 24 hours, where the collection takes place only during sunset hours, like in the case of solar powers. Okay, and system large buffer storage capacity to store energy per day or 2 years. And one storage basically for hydropower plants storage energy during the summer when production excessive demand. No, not only summer, in case of hydro, it stores in case of rainfall, and then when there is less rainfall in winter, then it can be used for producing electricity. Okay, so please see this graph very carefully. These are very important graphs. And basically, if we see the basic method for storing thermal energy, then sensible storage, you know, the amount of energy storage dependent on the temperature change of the material, like T1 minus T2 temperature swing. Latent heat is the amount of energy stored depends on the mass and latent heat of fusion of the material. Okay. Storage of bread has the melting point of the material. Then we have the thermochemical storage using heat to induce a certain chemical reaction and storing the butter. Then the heat is released and the reverse reaction is made to occur. Okay. So basically, thermal energy storage has three types: sensible, latent, and chemical. Sensible energy can be stored in these types like water. Water is the best because it's cheap and can store energy, but the main limitation is it can store the energy up to not up to very high temperature. The specific heat of water is quite high. And organic paraffin and paraffic and inorganic salt, eutectic or hydrate metal alloys and other components also. And these are the design considerations. Please have a look at this slide. This is very much important. If you have any questions, then please ask. So you guys have got a fair idea about heat losses from the storage that has to be kept in cost of storage. So basically storage capacity also depends on the availability of solar radiation, nature, thermal process, economic assessment of solar versus auxiliary energy, and physical and chemical properties of the storage media employed. So basically when we talk about the sensible heat storage, these are simple design and latent storage, because in latent storage the temperature has to be incorporated being basically sensible storage, and disadvantage of being bigger in size, and another thing is that it cannot store or deliver energy at a constant temperature. So exception is the water heat transfer oils from the storage. So yeah, basically when we talk of sensible heat storage, then this property like specific heat density, volumetric specific heat are the important properties. Okay, so when you see this volumetric specific heat criteria, that is heat that can be stored per degree Celsius rise and permit cube volume. So you see that aluminum has a very high aluminum concrete, rock river stays, stone. These are quite high. Water has the best volumetric 4180. Okay, so that is why I was saying the water can be used as a heat storage medium. So that is why when you see a lot of storage system based on water, okay, so it is low in cost. Water can be easily available. It has a high specific heat. Low space heating can also use water as the storage aspect of transport medium. So this you have to remember approximate thumb rule. If you don't know anything, 3 to 500 kg raw per square meter per area is referred to as basic. Okay. So now solve this numerical. Okay. Let's solve this numerical. Let's solve this numerical. So when we try to apply this question, the solution. When 270 liters, so convert it into kg. Okay. So first thing when this type of question is given, first thing you can do is convert it into kg, because the CP value is in kilojoule per kg per degree Celsius. Okay. So first try to get the del T, that is 55 minus 15 to 40 degrees Celsius. Then for 270 liters, take density of hot water as 993 kg a centimeter cube or meter cube. Sorry. Okay. So and CP is 4.18 kilojoule per kg. Now Q equal to okay, so this is the energy required. And this is what asking in the question. Have a look at this. please have a look at this, and if there are any queries, feel free to ask. Okay, so if you cannot understand any of these, this is a very easy question that can be solved. Okay, so let's change this value to 60 and change this to 25. Now calculate me the amount of the energy required. This Did you solve it? No? Yes, and discard. Let me see. Akhil, I cannot explain this question 11 because week 11 is running assignment and we have been actually, yeah, we have been strictly forbidden to discuss the assignment questions. And yeah, so Akhil has asked, okay, so he has calculated 39.224 kilowatt. Okay, so let's see and how to convert liter to kg. It's simple. Liter is basically 1 liter is 0.001 meter. Okay, so you know the meter cube, you can multiply it with density to convert it. Okay, so now let's solve this. Let's see whether his answer is correct or not. I wanted to see whether his answers are correct. So yeah, so I have changed it to like 10. I don't remember it, and this is 60. So similarly, Q equal to 270 to 993 into how much is delta T? 60 minus 10 equal to 50. Okay, into 4.18 is the MCP delta T. It's simple MCP delta T. Okay, here M is the mass, CP is the specific heat, delta T is the temperature difference. And yeah, multiply it and divided with 1. So it comes to be 56034.99 kilojoule. Okay, so if you want to convert it to kilowatt hour, it will be something around divided by 3600, 15.656 kilowatt hour. Okay, so I don't know how much Akhil has got. Akhil has got something 39.224. So that is wrong. Akhil, you have done some mistake, I think. Okay, so now let's move to the next. So basically, I am focusing on questions. Now, if you want to see the energy balance analysis of liquid tank storage systems, so if you want to see the energy balance, you can also equate the energy that is coming and then what is leaving equal to zero. So that is how you can get it. Okay. So if you So this is the question. So now let's discuss it. Well mixed water storage unit contain 3100 kg of water and is provided with auxiliary heating of 3 kilowatt. So the configuration. Okay. So this is the auxiliary heating. Okay. Data for useful heat can from the collector ambient temperature and rate of withdrawal to the load on a particular day from R as follows. Assume the auxiliary heater switches on when the temperature tanks fall below and make up water at 24 degrees Celsius and enter the same rate at the rate of withdrawal of the load. Calculate the hourly variation of TL from this, starting the value of time that the auxiliary heater switches on. So this is what you need to calculate. So so heat capacity of the liquid rho BCMCP 3100 into 4.18. This is the heat capacity that is for water. and TL at 3 am was 50. Okay. Now you have to calculate the TL at these temperatures. So how will you calculate? Q load equal to M load into CB TL minus TA. So for 3 to 4 hours, Q load equal to 200 net mass into 50 minus 60, that is starting point minus 16. This is the heat. Okay, so similarly we know Q minus Q load UA into TL minus T equal to this. So put the values, you will get TL at 4 am equal to 47.65. So it won't be similarly for 4 to 5 hours. Q load equal to this much. So multiply, putting the values, still at 5 am the values are 45.46. So 5 to 6 am the values falls below 43.79. So and for 6 to 7 this comes to be this. Okay, so temperature has been between 5 to 6, you see this. So heater remains switch on after 5 hours for 13.30 minutes. Okay, so this is what the basically melting point and heat and fusion of typical phase changing materials. So these are phase changing materials. So what is phase changing materials? Something which changes phase with the material. So these are basically latent type of storage. So these changes phase like ice and water. So ice will gain heat, changes to water. Water when loses heat changes to ice. So these are phase change material. So there are various type of phase change material which has been listed here. So these are very important actually. So these are generally phase change material are quite costly in nature. So there can be question in the exam like arrange it in terms of heat of fusion. So please have a look at them. So these can be asked in the exams. Okay. So basically we will study a solar pond. So solar pond is a very interesting concept when you see. So whatever sun rays is coming from sun, so it basically heats the upper layer, and basically when it heats the upper layer actually acts as a insulation zone. So whatever heat that penetrates down is actually stored. So if you pass a cool water through this tube, it can gain heat and then hot water can be out. So these can be a very interesting solutions and ready for salt water. Salinity is high. Okay, so these are very interesting facts. The maximum temperature of 100. Why a maximum temperature of 100 can be obtained? So can anyone answer it? Why only 100? Why not more than that? Because water generally heated up to 100 and then it converts to steam. Generally, in case of solar plant, maximum temperature 100 can be obtained. So basically, so let's solve this question. Okay. So basically, this question says that sodium chloride is used as salty solvent to estimate the minimum concentration required at the bottom if the concentration at the top is 0.02 and a temperature difference of 65 degrees. Temperature on straight lines and average values of dp by dt. And so basically, you have to fill it in there. So dp by dt average value 0.5, dt by dx you have to look at dp by dc, that is concentration. Uh, Density with consideration kg per meter cube. With this, you get dc equal to 0.5 upon 650 into dt. Okay, so basically dx got cancelled. So dc, what is dc? C2 minus c1, and what is the dt? dt is 65 degrees Celsius is given temperature difference. So multiply it. C2 minus c1 is given. C2 is 0.07. Okay, how 0.07 can come? Basically, we add C1 to this. So C1 is 0.02 initial concentration. So yeah, this is the kg of salt per kg of water. Okay. So there are basically thin zones: surface convective zone SCZ 10 to 20 centimeter thickness. Then we have concentration gradient zone, half of the depth of pond. And then we have lower convective zone. So useful heat is only 14%, okay, and heat loss is 2% and 84% is heat loss to the atmosphere. It's not a very highly efficient, but yeah, it can be used for generating a temperature, high quality of water. The solar power generation can work like this. So I won't go much detail into this. Okay. So these are the questions which you have to remember, because question most of the numerical can be solved based on these type of questions. Okay. So have a look at this slide. Then I will discuss the concepts. So transmitting based on absorption and uh, 76% of radiation is accounted. So basically, when we talk of this transmittivity based on absorption, so let me see if there are any questions who can't understand. So we'll solve this question. Okay. So basically what I was talking about is that key you need to understand these type of questions. So when you understand these type of questions, it can be very easy for you guys to solve basically the questions. Okay. So a 2 meter deep solar pond is built in Guwahati. So let's solve a question. So a 2 meter deep solar pond is built in Guwahati. The values of global and diffuse radiation measured on a horizontal surface on 15th May at 13 hour are 900 watt per meter square and 200 watt per meter square respectively. So calculate the flux reflected from the water surface and flux entering the water and solar flux at the depth of this. So I should here only I can take a laser pointer. So on May 15 you can calculate the n, what is 135, and phi, which is basically based on the latitude angle 26 plus 8 by 60. Then we have delta 23.45 sine 360 upon 360 by 284 plus 135. So when you have all this, you can calculate the cos theta 1. Okay. So after calculating the cos theta 1 sine theta 1, okay, and this is also given for beam radiation. Agree? So based on this, you can get these values from the table itself. And then flux reflected from the water surface can be calculated as we have seen in the previous slides also. The flux entering the water, that is whatever is reflected. So whatever is coming and reflected, so flux entering the water, you can be calculated. So transmitting based on absorption is T alpha equal to 0.36 minus, that is the law which we have seen here. Okay, so you use this value. So based on the transmittivity, you can calculate the different solar flux at various depths. So for depth of this one, you can calculate the solar flux. So you can see with depth, the solar flux is actually getting down. Okay. So this is what can be represented here. So incident flux was 900, then it goes down and down as the water depth increases. So you can easily see the penetrating power and solar flux, and also the temperature distribution can be calculated with the solar flux. So not going into much detail. So there are some shortcomings. So there can be question on this. So these are also theoretical portions are also important. Okay. So this is what the different solar ponds. So we have a solar pond in Gujarat, India. Then the biggest solar pond, 150 kilowatt in Israel. The main problem is that they require a large area. Also, so existing ponds can be converted and used as solar ponds. Okay. So now we will discuss the assignment questions. Okay, so let's discuss the assignment question then. So question one is basically capacity of a sensible heat storage system depends on the so basically when you are talking about sensible heat storage system, so first thing is that key will have a temperature term. Okay, so basically Q equal to the capacity m cp del T. So temperature is the key. Then we have mass also, mass of the material. Then specific heat of the material is also, because when you see the specific heat of the water, it's 4.18. But when you see a specific heat of ice or something, then these are quite less compared to water. So these all of the four actually affects the capacity of the sensible heat storage system. In case of non-convective solar pond, the bottom surface attains the dash temperature. So likewise, we discussed the solar pond. So basically, this is reflective layer, then there is this layer, insulating layer, and the bottom layer which is has the maximum temperature. Well, because insulating layer is above it, it protects the heat from going outside. So it attains the maximum temperature. And basically I have put this here for aquifers thermal storage, like how the thermal storage can be worked out in aquifers. So basically heat here can gain the heat, and then in cold time, in sunny time, it can gain the heat and store it, and then cold time it can supply for the building. Okay, similarly sensible heat, latent heat, and this thermochemical. So basically sensible heat is increasing of temperature, latent is basically increasing temperature. This is sensible part, this is sensible part, and this is latent part that is stored. And we have thermochemical, that is heat stored in chemical form. The expression of stability criteria for solar pond can be given as, so we solved a numerical also now for a stability criteria like dc upon dx greater than dp upon dt upon c dt upon dx. So I think this one is the correct answer. Then we have an insulated tank that is filled with 550 liters of water having a density and specific heat of this, then thermal energy required. So see the question which we solved in the lectures also, like the same on the same pattern. So just go through the slides, you will be able to solve the questions. So similarly, just Q equal to 550. So first convert it into liter. Sorry, meter cube to 998 kg per meter cube to 4.2 and to del T, that is 71 is 25 is 45, and then you need it in kilowatt hours. So just do it. 550 into 998 into 4.2 into 45. So that comes out to be 103,742.1. Then to convert into kilowatt hour, you just have to divide it by 3600. So it comes out to be 28.817. That is 28.82. So this is the correct answer. So have a look at this question, how it has been solved. Okay, so, now moving to the question 5, the amount of energy stored in case of latent storage depends on. So latent storage, when you see the latent storage, it is basically not dependent on the increase in temperature, but at a specific temperature, the amount of energy that goes into changing the phase. So that is basically latent heat of fusion and mass, not the specific heat, because it's not a specific heat storage, not the temperature difference. These two are wrong. So correct answer is answer B. The design of a thermal energy storage system depends on. So basically, when you see a thermal storage, temperature difference is the key criteria. Second is capacity of the storage system. Third is the cost is also an important criteria. So all of the above is the correct answer here. The limitation of using sensible heat storage system are. So first point is it can't deliver energy at constant temperature. Okay. Bigger in size, simpler in design. This is the limitation. Bigger in size. Okay. And simpler in it is not simple and it can deliver. So this is also a problem because the basically it doesn't deliver energy at constant temperature. Energy temperature variation is how it stores the energy. So 1 and 2 are correct. And reversible chemical energy storage, the input energy in the form of, so basically in reversible chemical energy storage, the input energy is basically in the form of thermal energy. Okay, the chemical to thermal, thermal back to chemical. And then I want you guys to solve this question. Try to solve it. Okay, so did you guys solve? So desirable properties of each material are basically uh, high latent heat of fusion. This is required. This is not required because it's desirable property. So if there will be high latent heat of fusion, then it won't be able to actually store heat. Small volume change during melting because smaller size will be there. Minimum supercooling or superheating. So yeah, high thermal conductivity. No, this will promote heat losses. So correct answer is 2 and 3 are correct actually. Then we have thermochemical storage system are suitable for. So basically, they are suitable for low temperature applications. No, they are not suitable for low temperature application. They are suitable for medium temperature applications and high temperature applications. So correct answer is answer D. A solar pond is maintained with negative gradient and gradient due to concentration in this much. So if the concentration at the top is 0.04 temperature difference and the minimum concentration of the water required. So I think this type of question was also solved now. This you can use this formula here. Okay, so you can use this formula to solve it. And, I think this is given, this is given, so you have to just calculate dt and then dc equal to c2 minus c1. Del t is also given here, dx will be cancelled out. So that is how you will be calculating this. Okay, so try to calculate it. And this one is a big question. So this I think this also I have solved it with constant rate. How, what is the temperature water inside the tank at 8 hours. So yeah, this can be solved. This also the question was there based on these type of things. Okay, so the correct answer here is answer C. C. Okay, so let's say let's solve it. Dx equal to, so it's given 0.7 into del t upon dx, and this is dc dt 730 is given. Okay, so c2 minus c1, dx will be cancelled, minus 0.7 into this 75 dt upon 730. So this comes out to be 0.7 into 75 divided by 730. So this is 0.071. So C2 minus C1. How much is C1? 0.04. So this comes out to be here plus 0.04. So this is equal to 0.111. Is the correct answer? Answer A is the correct answer. Okay. So this is how it is solved actually. So similarly, you can solve every questions. Okay. So thank you once again for this live session 11, and we'll see again on Monday. That will be the last live session for week 12, and then there will be a summary session also on 18th. So be ready, and best of luck. Your exams are approaching, so keep revising the concepts and keep solving the questions. That will help you actually in gaining confidence also and solving the questions. Okay, so thank you all, thank you once again for attending this live session. So yeah, I'll cut this, stop the recording.